Hello everyone. Going to do a few more differential equations today. I don't know about you, but I'm relieved it's Friday. It's really Thursday as I'm recording this, but I can imagine. If you're watching this and it's not Friday, here's a consolation prize for you. Enjoy that. Today's lesson is brought to you by Schadenfreude. Schadenfreude is a German word that I'd have difficulty using in a sentence, apart from that one. Anyway.
Can't you see that on a t-shirt or a...
Hello?
So in our first example of the day, the area under this curve is 3/8 from a to pi over 2, and we need to figure out what a is. So where did this derivative come from? Well, it came from this expression, 1/2 sine x squared plus c, and that actually came up a few lessons ago. So if we were to figure out the area under this curve, assuming we knew a, we would evaluate this f at pi over 2 and subtract f evaluated at a. So if we did f at pi over 2 minus f at a, that result would be 3/8. So with this, we can just evaluate this expression when x is pi over 2. So we would have 1/2 sine at pi over 2 squared plus c, subtract 1/2 sine at a squared plus c, and that whole thing is equal to 3/8. Now c minus itself is 0, and sine at pi over 2 is 1, and if we square 1, it's still 1, so this whole expression first gives us 1/2 times 1, and this would just be 1/2 sine squared a, which is equal to 3/8. And now we can bring all the numbers to one side and then bring this to the other. So 1/2 minus 3/8 would give us 1/8, and that equals 1/2 sine squared a. And if we multiply both sides by 2 here, we would have 2/8 equals sine squared a, and 2/8 is equivalent to 1/4. So that's equal to sine squared a. Now we can square root both sides of this expression, which will give us sine a is equal to 1/2. Now thinking back to our unit circle days, sine is 1/2 when this argument is pi over 6. So a is pi over 6, and that's our final answer for example number 5. So on to our next example, number 6. A particle moves in a straight line and has an acceleration given by this function. Its initial velocity is this, and its initial displacement is this. Determine the position function. So with this question, we need to know how displacement and velocity and acceleration are related. So the derivative of displacement is velocity, and the derivative of velocity is acceleration. Or in other words, the slope of displacement is velocity, and the slope of velocity is acceleration. So what we basically need to do with this question is work backward from a and figure out what the displacement is. So first thing we need to answer, where did this derivative come from? So the answer to that question will be velocity. So this term would have come from a t squared, and in order for us to get a 6 out of that, we would have to have a 3 out front. And this would have come from a t term, and in order for us to get a 4 out of that, we would have to have 4t, and we should also have some constant, call it c1. Now we know the initial velocity at time 0 is -6. So if I put 0 in for these times, the velocity would be -6. So let's do that. -6 equals 3 times 0, which is 0, plus 4 times 0, which is also 0, plus c1. So that was easy. c1 is -6. So we can replace this c1 with a -6, like that. So now, where did this derivative come from? The answer to that question is going to be displacement. So this term would have come from a t cubed, and in order for us to get a 3 out of that, I guess we don't need to alter that at all. It would just be t cubed. So it would be 3t squared, which is what we need. Next, we would have 4t. So this should have come from a t squared term. And the coefficient needs to be 4, so that should probably be a 2 out front. And -6 would have come from a t. And we should also have a constant, because the constant derivative would be 0. So it wouldn't show up in the velocity. So given that the initial displacement when time is 0 is 9 centimeters, if I put t equals 0 in for all of these t's, the displacement would be 9 centimeters. So 9 equals 0 plus 0 minus 0 plus c2. So c2 is 9. And finally, we can answer the question. The displacement function is going to be t cubed plus 2t squared minus 6t plus 9. And now on to our final example of the day. In example number 7, an object is thrown from the top of a 140 meter tall building with an initial velocity of 15 meters per second, maybe assume up. If the acceleration due to gravity is approximately negative 10 meters per second squared, then determine the following. So first we need to determine an expression for velocity. So to start, the acceleration is negative 10 for all of time. That's constant, at least while it's in the air. And where did this derivative come from? That would be velocity, which needs to be negative 10t plus some constant, maybe call it c1. Now we have the initial velocity is 15 meters per second, and we're assuming up, so velocity at time equals 0 is positive 15. So when t is 0 here, v is positive 15. So 15 equals negative 10 times 0 plus c1. So basically c1 is equal to 15. So our velocity function, v of t, is equal to negative 10t plus 15, which may look familiar to you if you took Physics 20 last year. A is delta v over delta t. So we could express delta v as vf minus vi, and then this turns out to be vf, this is vi, and this is a times t, or a times delta t. Next we need the velocity of the object 1 second after release. So that would be v at t equals 1. So we plug 1 in for t here. So negative 10 times 1 plus 15. So 15 minus 10 is positive 5 meters per second. Next we need to determine the maximum height of the object. So the maximum height happens when v equals 0 momentarily at the top before it starts going back down again. So first, v equals 0. We have an expression for v already, negative 10 times t plus 15. We can solve for t, and t equals 1.5 seconds. So when t equals 1.5 seconds, the speed is going to be momentarily 0 at the top. So second, what we should do is s prime equals v. So the antiderivative of v gives you the displacement. So where did this derivative come from? First off, this term should have come from a t squared. And if we do t squared derivative, it would be 2 times t. So in order for us to get a negative 10 out of that, we can maybe divide by 2. 15 would have come from a single t plus some constant c2. So before we continue and determine what the maximum height is, we need to figure out what c2 is first, and we'll need some extra information. So at time 0, the initial height is 140 meters. So with that, when time is 0, the height is 140. So we can sub 140 in for s and 0 in for t, and basically we figure out that c2 is 140. And now we have a complete picture of the displacement function. So if the maximum height occurs at t equals 1.5 seconds, all that remains is to sub in 1.5 in this expression, and we get our max height. So s at 1.5 is negative 5 times 1.5 squared plus 15 times 1.5 plus 140, which is negative 11.25 plus 22.5 plus 140, and that eventually gives us 151.25 meters. Now if you think back to your physics days, those kinematic equations, this may look a little familiar. You may recall the equation d equals vit plus 1/2 at squared. So you remember those 5 kinematic equations we used so often that was on our formula sheet? Well, guess what? We don't need them anymore. Physics is a lot easier with calculus. So next question, D. In this question we need to determine the velocity when it's 50 meters above the ground. So at 50 meters above the ground, what time is that? So we can start with our displacement function. 50 equals negative 5t squared plus 15t plus 140. And if we solve this equation, that's going to give us a time when the object is 50 meters above the ground. So we can bring 50 over. So we would have negative 5t squared plus 15t plus 90. We can factor a negative 5 out of these terms. So we would have negative 5t squared minus 3t minus 18. We need two numbers that will multiply to give negative 18 and add to negative 3. So we would have t minus 6 and t plus 3. Now this would give a time of minus 3 seconds, which doesn't really make sense in this context. So we're going to go with this one, t equals positive 6 seconds. So that is the time when the object is 50 meters above the ground. So now we just need to figure out what the velocity is at 6 seconds. So we use our expression for velocity and put a 6 everywhere we see a t. And finally, we get negative 45 meters per second. That's the velocity when the object is 50 meters above the ground. Now the last part, E, what's the velocity of the object as it hits the ground? Well, as it hits the ground, displacement is 0. So we would start with the displacement function when it's 0 and figure out what time that is. So negative 5t squared plus 15t plus 140. We can factor again a negative 5 out of these terms, leaving us with t squared minus 3t minus 28. So we need two numbers that will multiply to give negative 28 and add to give negative 3. So that'll be negative 7 and positive 4. Again, this will give a negative time, which doesn't really make sense in this context. So the time when it hits the ground is going to be 7 seconds. So now we just need to figure out what the velocity is at 7 seconds. So velocity at 7 is negative 10 times 7 plus 15, which will eventually give us negative 55 meters per second. So please try these questions out now. I'll get you to do this one in particular. And that's all for today. See you next time.